Have you ever just stared at your computer and wondered how? Seriously, how does it do all that stuff at once? Well, today, we're going to pull back the curtain on the invisible magic that powers our entire digital world. Okay, let's dive right into the evolution of operating systems.
It really all comes down to this one question, right? It feels like our devices are genuine masters of doing a million things simultaneously. But the secret? Well, it's not magic. It's actually a series of brilliant ideas developed over decades, all to manage a computer's most precious resource, its processing power.
So, our story starts way back in the early days, when computers had just one single brain, a single CPU. And the first big challenge was figuring out how to stop that one brain from ever getting, bored.
See, the core problem was that CPUs are lightning fast, but other things, like reading from a disk or waiting for you to type something, incredibly slow in comparison. The CPU would finish a task and then just sit there, wasting time. Multiprogramming was the genius solution. If one program is waiting, just give the CPU another program to work on.
And this is basically how it worked. The operating system would load several different jobs into the computer's memory all at once. So if job 1 needs to wait for, say, a download to finish, boom, the OS instantly switches the CPU's attention over to job 2 or job 3. Absolutely no time is wasted. It's constantly working.
So, the huge win here is that this dramatically boosts efficiency. You just get more work done, period. But of course, it comes at a cost. The operating system has to be way smarter, way more complex, and you suddenly need a lot more memory to hold all those jobs at the same time.
So we solved for pure efficiency, getting the most raw work done. That's great, but what about the user? The person actually sitting at the desk? For you, it's not just about efficiency, it's about how fast it feels. We needed to create the illusion of an immediate response. And that brings us to multitasking. It's this really clever refinement of multi-programming. Instead of just waiting for a program to get stuck, the OS forces every program to share. It gives each one a tiny little slice of time, they call it a quantum, and then it switches to the next one and the next one, so fast it creates this totally seamless experience for you.
This is exactly what's happening on your desktop right now. Your browser, your spreadsheet, your video player, they all want a piece of the CPU. The OS is like a traffic cop, giving each one a tiny turn over and over again, so incredibly fast that to you, it looks like they're all running at the exact same time. It's a beautiful illusion.
Okay, so making one CPU hyper-efficient is fantastic, but eventually you just hit a physical limit. So what was the next logical step? Well, if you need more power, you add more brains.
And this, my friends, is multiprocessing. This isn't an illusion anymore. We're going from one chef in the kitchen trying to juggle a bunch of different recipes to a whole team of chefs, each working on a different dish at the exact same time. This is true parallel power.
And just look at this architecture. You've got multiple CPUs, and each one has its own super-fast local memory, its cache, but they all share the main memory. This is what lets them work together, to collaborate on really complex problems, and it dramatically increases the whole system speed for those heavy-duty tasks. The advantages here are pretty obvious, just immense speed. And even better reliability, because if one processor fails, another one can often just pick up the slack. The downside? Well, it's expensive, and coordinating all those CPUs is a serious engineering challenge. All right, so far, everything we've talked about has happened inside a single box. But what happens when the power of one machine, even one with a bunch of processors, just isn't enough? Well, you connect them all together. This right here captures that next huge conceptual leap perfectly. On the left, that's multiprocessing, multiple brains in one body. But on the right, that's where we start getting into distributed systems, a whole team of separate computers connected by a network, all acting as one single unit. So, the first step in this direction is the network operating system. Just think about your school or your office network. There's always that one central server that acts as the boss, right? It's managing who gets access to files, to printers, and all the other shared stuff. And here's the classic model for that. You have all these client computers, and they're all talking to one central authoritative server. That server is the absolute heart of the operation. Everything depends on it. But a distributed OS, that takes it a step further. The goal here isn't just to share some files. The goal is to pool the processing power of many computers and make them appear to you, the user, as one single incredibly powerful supercomputer. You don't know, and you don't even care, which physical machine is actually running your task. The real power here is just massive scalability.
Need more power? You just add another computer to the network. Simple. But its greatest strength is also its biggest weakness. If the network that connects all of them goes down, the entire system can just grind to a halt.
Okay, let's switch gears for a second. So far, we've been focused on speed and efficiency. But for some systems, the most important thing isn't being fast. It's about being on time, every single time.
Welcome to the world of real-time operating systems, or RTOS. In these systems, a late answer isn't just late, it's a wrong answer. There are no do-overs. The response time has to be absolutely guaranteed.
And the distinction here is absolutely critical. In a hard real-time system, like a car's airbag, a delay of even a few milliseconds means total system failure. The deadline is absolute. But in a soft real-time system, like when you're streaming a video, a slight delay or a moment of buffering, yeah, it's annoying, but the whole system doesn't catastrophically fail.
So we've traveled all the way from a single, simple CPU to these vast networks and systems where timing is literally everything. So what's the big takeaway? This isn't just abstract theory. This is the code that is literally running your life. This entire evolutionary journey is happening all around you, right now. That incredible efficiency of multi-programming, it's what powers our financial systems. That smooth, responsive feel of your desktop, that's a blend of multitasking and multiprocessing. Your office network, that's a network OS. And the life-saving technology in your car, that depends on a hard real-time OS.
So the next time you pick up your phone, a device with multiple processors, juggling dozens of tasks, streaming media in soft real time, all while connecting to global networks, just think about this whole journey. How many of these incredible, world-changing ideas are working together in perfect concert right there in the palm of your hand?